Hi everyone, in this video I'd like to introduce a quick demonstration of this important theorem in mathematics called Fundamental Theorem of Algebra. So what this says is that all the polynomials, doesn't matter if it is degree 3 or degree 2014, whatever, all the polynomials whose coefficient are complex numbers, then they have zeros in the complex numbers. This imaginary number I, such that its square is assumed to be -1 in the real line, is, I think, is introduced to take care of the quadratic equation, such as x squared plus x plus 1, x plus 2 equals 0. If you sketch this polynomial and there's no real number that makes this equation exactly 0, it's going to be a parabola. It's hovering over real axis like that, so there's no real number that make this polynomial 0. But if you look at the quadratic formula, the quadratic formula says x is supposed to be 2 times a, which is the coefficient of x squared, minus plus minus root of b squared. Here is 1 minus 4 times ac. So it has this negative number inside. So if you have square root of -1 in our number system, then we can take care of all sorts of root of negative number inside there. I think that's the very motivation of imaginary number kicking in. But in the history they begin to detect that we introduced this imaginary number just to take care of these quadratic equation, but they realize that one at a time this number system, complex number, usually denoted by this boldface C, all the polynomials we consider happen to have solutions within that. So that's a bit of surprise, and that is actually became a theorem. And the rigorous proof really passed the big mathematicians, Euler, Gauss, and Legendre, and all those people, and the rigorous and perfect proof was given in 1800. So to understand this theorem, let us review about the complex number, usually denoted by the z, and this a is usually standing for real number, and b is another real number multiplied to this imaginary number we created to take care of quadratic equations. But if you look at the arithmetic of this number, this type of number multiplied and subtracted and divided each other, they always look like this. So after went through all sorts of arithmetic, they still can be arranged into this form, a plus bi. A is real and b is another real number multiplied to that. It's separated like this. They realize that it's actually better to represent it's a single complex number using two real numbers, a and b. So this is actually, this horizontal axis is representing all possibilities of this part, what we call the real part. Y coordinate is representing this part here, coefficient of imaginary part. So if you're looking at 1, 1 in xy coordinate plane, that actually corresponds to 1 plus 1 times I, the single complex numbers. So this entire xy plane is representing all the complex number denoted by usually this boldface C. Thinking about a function such as z squared plus z plus 1, before we looked at only z with the real numbers, now we're looking at all sorts of numbers in here, and every time we plug in this number and multiply it to itself and add it to itself and plus 1, you can reorganize it to this form again. So that's what's happening to this polynomial. So the difficult part of understanding what the function is doing to complex number, or understanding the graph of the complex numbers, is that our domain, the one variable c and z within this complex number, takes up this 2-dimension, and we'll go through this. For example, this polynomial z squared plus z plus 1, and then instead of y equals x squared plus x plus 1, we're now writing a w equals z squared plus z plus 1. So this is a single complex number, and w is represented over here. So we have to draw the duplicate of this xy plane. They're living in a completely separated world, or maybe we should do this d and c. These are the real part and imaginary part. You can rearrange it to c plus di like this always, but z look like a plus bi in there. So if you choose a point in here, whatever that a comma b, which is really in complex number form, is a plus bi. So went through this arithmetic, rearrange it into real part and imaginary part like this, and go to somewhere here and c comma d, which is really corresponds to this complex number, c plus di. So each position in here is going to be mapped to some of the position in there. So it's kind of a natural, because it's a natural function, it naturally deform or transform these grids of this xy plane into here. So the key thing to understand what this function is doing to this AB plane is that looking at the circle, if you especially look at the circles, and it helps us to understand why this fundamental theorem of algebra is true. So let me first mention what this 0 means. For example, if a comma b is mapped to over here, which is sketched over here away from the 0, so this is not the number we're looking for. It's not a 0. That means this complex number went through this complex function, this polynomial, it didn't go to 0. If you say a 0, we have to find some mysterious value over here, so I'm going to call a prime, b prime, such that this value, after you go through this quadratic expression, this maps exactly to 0. This is where 0 plus 0i is, and this is the 0 in the complex number. All the other numbers, even over here with x coordinate 0, this is not 0 in the complex number. The only 0 in the complex number is 0 plus 0i. So we have to find some position in here. After you went through calculation, you had to arrive exactly in that position there, right here. So that's a 0. So we have to guarantee that no matter what polynomial you look at, there will be some position. So it's going to arrive at here after you go through that polynomial. This is not going to be a rigorous proof. We're just going to use a polynomial to demonstrate what happens here. The polynomial, that degree is more than 2. So here I made a change. Instead of z squared, I changed it z to the 4th and plus z plus 2. So first I'm going to show you how this function looked like on the real line, not on the complex numbers. So I sketched it here with Mathematica that how that function of the degree 4 function looked like. Although it's only showing in between -2 and a +2 here, it is actually true. If you look beyond the -2 and a +2 here, it'll never come back down and cross x-axis. So if that's true, and it is not crossing visually here in between -2 and a +2, so it does not have real solution. But fundamental theorem of algebra says that there is going to be complex solutions. So this part here is a demonstration of the complex plane going to the complex plane. So this is where the complex number z lives, and this is where a complex number w lives. So let me change the cursor. Alright, I think I changed the cursor. So this means here is the complex number 0, the z is 0, and under that map it is going to 2 here. Remember, the constant term of the polynomial z to the 4th plus z plus 2 is 2. So if you plug in z equals 0, that goes to 2. So that's what happened. So if I increase a little bit, it shows that we're looking at not everything, just a complex number around the 0 here. So if I send this one, which is pretty much 0.2 or something, that will go to somewhere here. And if you try all the other values in here, they land in somewhere in this circle in here. This red one is a target. We want to figure out somewhere in the complex plane that's going to hit the 0. So that complex number goes to 0, and that's what we want to guarantee. So if I play with this theta, it shows that as I go around the circle, that's what happened to the W part. It looks just another circle, but if I increase the radius a little bit, it changes. Although I'm sending this complex number with kind of radius fixed here, what happened after you go through that degree 4 polynomial, that W value is doing this crazy thing. It's going around like this. But it's getting closer and closer to 0. So as I increase this radius, it always, mathematically, in all cases, you can kind of guarantee that the maximum radius of this one increases as well. So as I increase more and more, eventually you can see it's almost about to hit the 0. So I'm going to go ahead and kind of pretend that this is the case where it hit the 0. So if you look at R value, so when R is roughly 1.078, and then here and somewhere in this angle theta, it's going to hit that point here. So if I play with this angle theta, you can see that retracts and figure out and exactly what angle is going to hit that 0. For example, somewhere in between here, if I look at the theta value and around 2.53 radian, around that value, this complex, whatever this radius and theta value is, this is rough location of complex number z under that function is going to map closely to that 0 in here. So the qualitatively, if I send this one back in here, if I increase it further and further, you can see its images of the z under that quartic functions. This radius, minimum maximum radius, is getting bigger and bigger, so qualitatively kind of eventually passes this point here, such that you can guarantee that, although it's difficult still to compute exactly where it is set to 0, but it was roughly about here, but qualitatively kind of guarantees that if you assume lots of things, that you can kind of see that where it passes through. And this is a lot better than just, telling you that there is a complex solution. This is a very good explanation of where roughly the complex 0 is located. So let me show you the theorem again. So there's the theorem. Whatever the polynomial you consider after you go through, as you look at a larger and larger circle, which are a collection of points in this part in here, it will eventually pass through the 0. So that guarantees the existence of 0, and that's one way to understand why this fundamental theorem of algebra is true. Thanks.